Welcome to the 7th week of live interactive session on the course Integral Transforms and their applications. So this week we will see two specific transforms, the Hilbert transform and the Stieltjes transform. So they are related or they have identical form. So without wasting time, we'll go to the demo problems. So I will show how to solve them, which may help you understand the concepts better and solve your assignments with ease. Okay, so let us start. So which of the following is or are the Stieltjes transform of the function f of t, which is t raised to alpha minus 1 divided by t plus a. So here alpha is a real number and similarly a also a real number. So I haven't mentioned them, but okay, let me write that. So alpha is a real number. Similarly, a also a real number. Thing is that a can be any real number, but alpha has some restriction, so that only the Stieltjes transform exists or it converges, because anyway it is going to be the definition is an integral, right? So I guess all of you know the definition. Let me write it. The Stieltjes transform of any function f of t, let's say from the variable t to z we are writing. So then there should be a function of z. Let me represent that as capital F of z. So this should be f of t divided by t plus z dt integral 0 to infinity. So here z is any number, okay, can be complex also, doesn't matter. So this is the definition of the Stieltjes transform of the function. So here if you see, if you substitute the definition, it's 0 to infinity, so t raised to alpha minus 1 by t plus a, that's the function f of t. Then the kernel of the transformation is 1 by t plus z times dt. It integrated from 0 to infinity. So here remember that a can be any real number. Similarly z also. Complicated thing is that about alpha, because if alpha is integer, then we can do a partial fraction and simply modify it, the function. Of course, one thing to remember is that if alpha is see, the numerator has alpha minus 1 and the denominator which is basically having t plus a times t plus z. So the order of in the large time limit, or sorry, when the t tending to infinity limit, so the order of the denominator is t square, and the numerator, the order is always alpha minus 1. So if alpha minus 1, the numerator goes like t raised to alpha minus 1, denominator goes like t square for any finite value of a and z when t is very large. So this we can rewrite it as alpha minus 3, and we are trying to integrate it when t is tending to infinite limit. Okay. So one thing to note here is that we know this kind of an integral will exist only if alpha minus 3 is greater than okay, let me write in the denominator. It's t raised to 3 minus alpha, right? So now you may recognize this. So this will converge only if 3 minus alpha is greater than 1, right? Because when it is 1, the 3 minus alpha is 1, it's dt by t, whose integral is log t. In the limit t tending to infinity, it's log infinity, which is a divergent quantity. So that's why I told, so basically this should be, the quantity 3 minus alpha should be greater than 1, so that only this will converge. Or in another way I can say alpha should be greater than, so alpha should be less than 2, then only this integral will converge. Okay, so this is the general thing. So you cannot say alpha is any positive value, but we have to have some restrictions on alpha, so that only this integral will converge. So what we'll do is, another thing to remember is that alpha is not any integer. I mean, it's not only integer, it can generally be any real number, right? So let's say alpha minus 1 is 0.5. So in that case, alpha will be 1.5. Or let's say alpha minus 1 itself is 0.5. So you will find it is a root t divided by t plus a times t plus z dt integral 0 to infinity. And see, this kind of integral we cannot easily perform using real calculus. We have to go to complex calculus. I mean, at least probably for root t you can do, but let's say this is alpha is some other real number, let's say pi minus 3, something like that. It's an it's a transcendental number, so you cannot do this by real calculus. So better you have to go to the complex domain to do the integration. So before going there, so this integral I can split it into, I mean, of course I can use the partial fraction method here and split it into two parts. What I can do is, so this 1 by t plus a times t plus z, I can write it as a divided by t plus a plus b divided by t plus z. Remember, a and z are just numbers. The integration variable is actually t. So in that case, I can find a is equal to 1 divided by or minus 1 divided by a minus z, and b is equal to 1 divided by a minus z. So the, let's say this is expression 1 for the Stieltjes transform. So from the expression 1, I'll get f of z, the Stieltjes transform of the function, which is the integral 0 to infinity. So t raised to alpha minus 1. See, when I performed the partial fraction, I taken out the t raised to alpha minus 1. I didn't include that. So only the 1 by t plus a times 1 by t plus z, that only I have did the partial fraction, right? So the coefficient a and b have commonly 1 by a minus z, it's common for them, so I will take it outside, which is a constant. The remaining part will be minus 1 divided by t plus a plus 1 divided by t plus z, then dt, and the constant is 1 by a minus z, which I can write outside the integral. Okay, so this I can rearrange a minus z inverse and expand the integrals 0 to infinity t raised to alpha minus 1 by t plus z dt minus 0 to infinity dt. Okay, before that let me write, yeah, t raised to alpha minus 1 dt divided by t plus a. So this is the Stieltjes transform, that what we want. See here, the two integrals that we need to perform, they are actually identical. It's just that the numbers, the parameters z, one integral has a parameter z and the other one has the parameter a. So let me call this as I1, which is going to be a function of alpha and z, and let me call this as integral I2, which is a function of alpha, and in place of z I just need to replace it with the a. Basically both integrals are identical. So if I find the expression for one of the integral, I can just replace it with the a with, let's say I evaluate I2 of alpha a and replace a with z, I will get I1. So basically both are I don't need to distinguish them with 1 and 2 because they are just the same integrals in the functions with two different parameters. So I had to go to complex plane, of course, to evaluate this integral. So one thing that you may get confused is that, see, the integration variable is actually t. So if I move to the complex plane also, still my integration variable remains t, and usually you will use z as a complex variable, right, in the integration. So if I bring z there, you may confuse with that z with the t, which is actually our integration variable. So I want to avoid that, so I'll just evaluate the integral I of alpha comma a, which is 0 to infinity. Okay, let me call this expression as 2. We will come back to this. So what we want to evaluate at this moment is t raised to alpha minus 1 dt divided by t plus a, whose integral from 0 to infinity. So to do that, let's consider another integral. Let's say I call it as j, which is a complex integral, a closed contour integral, t raised to alpha minus 1 by t plus a dt. Remember, t is now a complex variable, and I need to perform this integral. So we are going to use the techniques in the complex analysis to evaluate the integral. Let's say this is integral 3. For that, we need to extend this integral to the complex domain. That's what I'm doing the next step, defining a new integral j for the same function, t raised to alpha minus 1 by t plus a dt. But now t is extended to the complex domain and performed over a contour. The contour I will specify. So let me first draw the complex plane. So here we have real of t in the x-axis and imaginary of t in the y-axis, and the origin is there. And for this function, t raised to alpha minus 1 by t plus a, let's say a is a real number, let's say it's positive. So in that case, minus a, which is a negative number, is one of the singularity of the function. So this is the location of minus a, which is a singularity. And another singularity, does this function have any other singularity? So blindly you may say it is nowhere singular, I mean other than the location minus a. But see, alpha is any real number. So in that case, let's say alpha is 1.5. In that case, you will see t raised to alpha minus 1 is t raised to 0.5, which is square root t. Now square root t has a branch point at 0. So 0 is a branch point. And another branch point is there at infinity, and you have to connect them through a branch cut. And you can choose any branch cut, but here our integration we are going to perform from 0 to infinity. So best choice is the real line 0 to infinity. So we connect the branch point at infinity through the branch cut which is passing through the real line, which is 0 and infinity. So I have explained this only for the case alpha equal to 1.5. But let's say alpha is some other value also. Let's say it's a rational number. Whatever number, you will find a branch point at t equal to 0, other than any integer value. Okay, if alpha is an integer, you don't find it. But if it is a non-integer, you will find t equal to 0 is a branch point. Similarly, infinity, and there need to be a branch cut which is passing from 0 to infinity in any direction in the polar axis. But we chose it to be the real axis itself because we need to perform the integral over that line. So now the obvious choice of contour, I don't know is it obvious, but let me tell how the contour look like. So this is a contour we are going to choose. So this is called keyhole contour. Okay, let me represent this contour. At the KH, And see the contour. Okay, let me represent its arrow also. We are taking the counterclockwise direction, so that this contour is including the singularity at t equal to minus a, and it's excluding all of the other singularities, which is basically the branch cut or branch point singularities. So inside the contour only t equal to minus a is a singular point. Okay, and what else? The larger circle has a radius of r, so that it is going to r minus r, then ir here, and minus ir here. These are the points, and we are going to take the limit of capital R tending to infinity. And the smaller circle, which has a radius of epsilon, so let's say this is epsilon, so that we are going to take the limit of epsilon tending to 0. So we will recover the integral that we actually need to evaluate. So the j integral that I have defined is actually performed over this keyhole contour. Now let me tell that this is arc 1, and this is arc 2. This is line 1, and this is line 2. So the integral of the function over the keyhole contour, actually it's a closed contour. I can split it into line integrals over arc 1, arc 2, line 1, line 2. And from the residue theorem, we should write it as 2 pi I times the sum of all the residues of the particular function, and you see, which is enclosed inside the contour, closed contour, which is keyhole contour. And you see there is only one singular point which is enclosed within the keyhole contour, which is at t equal to a. So it's a residue of the function t raised to alpha minus 1 by t plus a at t equal to minus a. So which we will come to. So let me represent this as equation 4. So first we have to evaluate all the left hand side part, which is integral over the arc 1. Of course, arc 1 is a circle, almost a circle. It is not complete circle, but almost a circle. But in the limiting process, it will be a circular arc, but excluding the branch cut. Okay. And we have to take the limit of r capital R tending to infinity. So let me start doing that. So yeah, so arc 1, so we have to take the limit of capital R tending to infinity, and we can say, okay, yeah, we have to take the limit R tending to infinity. T here is actually r e raised to I theta, which is actually a circular arc, where theta is varying from 0 to 2 pi. Okay, it's a complete thing, but we are excluding the fact that there is a branch cut. So we have to actually, 0 is not equal to 2 pi, because once it passes the branch cut, 0 and 2 pi actually separated. That's because of the branch cut existing there. So we cannot say that 0 equivalent to 2 pi. Usually in every periodic function we say 0 is equal to 2 pi, but for multi-valued functions like t raised to alpha minus 1, where alpha is a non-integer, you cannot say 0 will coincide with 2 pi. Okay, and alpha is an irrational number or a non-integer. Anyway, so here is the thing. So this is the integral, and in the limit r tending to infinity, we need to perform this integral. So the arc 1 integral of the function t raised to alpha minus 1 dt by t plus a. So limit r capital R tending to infinity, then t I will replace it as r e raised to I theta, the whole raised to alpha minus 1. Then dt, remember r is fixed, only theta is varying along the arc. Okay, So r is a constant, then e raised to I theta I d theta divided by t plus a, which is r e raised to I theta plus a. And now theta is going from 0 to 2 pi. Okay, now in the okay, this I can simplify, but see, in the limit of r tending to infinity, the r e raised to I theta in the numerator and the r e raised to I theta plus a in the denominator. See, a is not relevant when r is very large. In the limiting process, you can say the denominator is also r e raised to I theta for any finite value of a. And at theta, you will find that r e raised to I theta in the numerator and denominator will cancel, and this integral will be, again, limiting process, r e raised to r tending to infinity. I is a constant which is taken outside, then r raised to alpha minus 1, which is also a constant taken outside. The integral 0 to 2 pi e raised to I theta times alpha minus 1 d theta. Okay, now we don't want this value to explode to a larger, because r is tending to infinity. So two things can happen. If alpha is exactly equal to 1, we'll get some finite number, which is going to be, I think, 2 pi I. But if alpha is less than 1, okay, let me write it as 1 by r raised to 1 minus alpha. See, if 1 minus alpha, which is greater than 0, or in another sense 1 is greater than or alpha is less than 1, you will find that this integral tending to 0. So this is the limit that we are seeking. So if 1 minus alpha equal to 0, we will get this integral is actually a finite value, which is 2 pi I. But anyway, which is alpha equal to 1 is an integer value, but we are seeking like non-integer generic values. So alpha less than 1 is one of the restrictions that we are giving for this integral to converge. See, alpha equal to 1 you can also try. So I am just going with alpha less than 1 case. Alpha equal to 1 is a special case that you will find a different answer. So I am writing a generic case where alpha less than 1 and going with there is no contribution from arc1. Basically, in the limit r tending to infinity, you will find the integral over arc1 will vanish. Similarly, arc2. So there epsilon is tending to 0 is the limit, which is the radius of the smaller circle. Everything else is same. It's a t is now epsilon e raised to I theta, and theta. Okay, one other thing is changed is the orientation of this circle is now not from 0 to 2 pi, but instead it is pi to 2 pi to 0. So it's clockwise. So it's actually 2 pi to 0. Now the integral over arc2 of the function t raised to alpha minus 1 by t plus a dt is again the same method, epsilon e raised to I theta the whole raised to alpha minus 1. Now dt will be, epsilon is fixed, theta is varying, so epsilon e raised to I theta I d theta divided by a plus epsilon e raised to I theta. Theta is going from 2 pi to 0, again limit epsilon tending to 0. Now again, like I said earlier, there r was tending to infinity, but here epsilon is tending to 0. So the denominator, now epsilon e raised to I theta is irrelevant compared to a for any finite a value, and you will see this will be equal to or asymptotically equal to. Before that, one more thing, that limit of the integration can be reversed if you put a negative sign in front. Okay, the orientation is now changed. Numerator epsilon e raised to I theta will not cancel with the denominator, because the denominator is actually in this limit is just a, so which is a constant. Numerator epsilon e raised to I theta will join with epsilon e raised to I theta the whole raised to alpha minus 1 and become epsilon raised to alpha e raised to I theta alpha, then I d theta is there. So here, as I mentioned earlier, a is a constant, I is a constant, epsilon raised to alpha is a constant. It can be taken outside. but it's fine. I don't want contribution from this also. See, one thing is that if alpha is 0, I will find a finite contribution from this expression, which is, I think, is minus 2 pi I by a. Like for alpha equal to 1, I find a finite contribution from the earlier integral arc 1. But there are specific cases like alpha equal to 0. So those things you can try out. But I say alpha not equal to 0. But if alpha was greater than 0, then basically in the limit epsilon raised tending to 0, the epsilon raised to alpha will make this tending to 0. So that's the only limit I am taking. So alpha is greater than 0. Then the contribution from arc 2 is also going to vanish. You'll find this also tending to 0 in the limit alpha is greater than 0. So we have evaluated our contribution of arc 1 and arc 2. Now the remaining contribution is of the line 1 and line 2. So let's evaluate the contribution of line 1. So line 1, see, it's actually parallel to the real axis in the limit of epsilon tending to 0 and r tending to infinity. You will find this is exactly the real axis over which the integral that we actually need to perform. Just that it is approaching the real axis in the limiting process from the positive side, from the first quadrant. So now you can say it's actually a real axis. T is r, or let's say x itself. Okay, I'm not confused. Let's say r itself. R is a number which is going from epsilon to r. Epsilon is tending to 0, r is tending to infinity. So t is actually r, which is approaching the real axis from the positive side. So it's r e raised to I theta, but theta is 0, which is actually equal to r itself. When we go to line 2, you will see a difference. That's why I just mentioned this thing here. So anyway, the line 1 integral of the function t raised to alpha minus 1 dt by t plus a will be, we have to write the limit epsilon tending to 0, r tending to infinity. The integral, okay, t is actually r, right? So it's r raised to alpha minus 1. Then dt will be dr by r plus a. Now r is going from epsilon to r, and this will become the I, which we actually want to evaluate, I of alpha comma a. Okay, now we move to line 2, the contribution of line 2. Here also you can write t as r, but see, it's approaching from the fourth quadrant towards the positive real axis, basically that line. So it has an argument of 2 pi I. So that's why I told there is a distinction when it is approaching from the top and approaching from the bottom. You see this line, I guess you understand what I'm saying. Let me use a different color. Okay, let's say red. This line is actually approaching the real axis from the top. So it has a argument of 0. But this line is approaching from the bottom. So it has an argument of 2 pi. Basically, it's a line which is rotated 2 pi times. Angle is basically its argument is changed to 2 pi, from 0 to 2 pi. So it's rotated, and that's how it came to the fourth quadrant. Then it is approaching the positive real axis. So that's why we, because the limiting process, we need to keep it this way. So, but still, again, r, you can see the orientation, which is actually going from capital R to epsilon. Unlike line 1, the line 2 has an orientation. Line 1, the arrow is pointing right side. but in line 2 the r is pointing left side, so the integration should be performed from capital R to small epsilon. So the r should go from capital R to epsilon. Nevertheless, the limits epsilon should tending to 0 and r should tend to infinity. So I mean, one thing to note is that r raised to 2 pi I is actually r itself, because e raised to 2 pi I is 1. Is cos 2 pi plus I sin 2 pi. So it's just 1, right? So you may think there's no need of putting a 2 pi I there, but there's a catch, because alpha is a non-integer that will group with this 2 pi I, and that is how we are going to get the solution. So we'll see how that works. So if you perform the integral, line 2, t raised to alpha minus 1 dt divided by t plus a. So basically limit epsilon tending to 0, capital R tending to infinity. Now the integral is from r is from, okay, let me put the limits later. So first of all, t is r e raised to 2 pi I, the whole raised to alpha minus 1. Then dt, which is dr e raised to 2 pi I, the whole divided by t plus a, which is r e raised to 2 pi I plus a. Now r is going from capital R to small epsilon. So remember, the numerator, this e raised to 2 pi I can group with, I mean it's actually 1, but still it can group with e raised to 2 pi I the whole raised to alpha minus 1. In the denominator, e raised to 2 pi I is 1. I mean that does not have any relevance in the denominator, so it can be written as 1 itself. And again, once again, the integration limit is when you apply the limits of epsilon tending to 0 and r tending to infinity, the integration will look like it's going from infinity to 0. So we just want to reverse its orientation, so we make it 0 to infinity by putting a negative sign in front. And as I mentioned earlier, the denominator is just a plus r, or just r plus a, because there e raised to 2 pi I does not going to make any difference, but in the numerator it will. So it's basically r raised to alpha minus 1, then e raised to 2 pi I alpha minus 1, again that combined with the 2 pi I again, we will get e raised to 2 pi I alpha, then dr there. So if we take the constants outside, that's minus e raised to 2 pi I alpha, then the remaining term, which is 0 to infinity r raised to alpha minus 1 dr by r plus a, we can tell it is minus e raised to 2 pi I alpha. Then the remaining is basically the same I that we have wrote earlier, it's I of alpha comma a. Okay, so so the catch is, like I said earlier, if alpha was an integer, then whatever before the I in this particular integral is just exponential of e raised to 2 pi I alpha. For any integer value of alpha, you will find this is x equal to 1, let's say alpha equal to 0, alpha equal to 1 or 2, whatever, you will find that exponential term is going to be simply 1, and you will find the entire expression is just minus I of alpha comma a. And when you combine with the line 1 and line 2, so as per equation 4, you need to add basically as per equation 4, you need to add line 1 and line 2 expressions. So there you will see that if that exponential term was 1, you will find the contribution from line 1 and line 2 will cancel, and we will not have any term which is involving the integral that we need to perform. So that's the issue. But for a non-integer value of alpha, we will find that this term is not 1, so that there is a finite contribution contribution of the integral I exists, and which we can rearrange and get it back. That's what we are going to do. So let's go to equation 4 and find what is there in the left hand side. Okay, let me do one thing. So we have evaluated all the quantities on the left hand side, the contribution from arc 1 to line 1 and line 2. Now the contribution in the right hand side only we need to evaluate, which is 2 pi I times the residue t raised to alpha minus 1 divided by t plus a. Okay, let me evaluate that. So 2 pi I times the residue of the function, which is t raised to alpha minus 1 by t plus a, when t is equal to minus a, because the singularity exists at the location t equal to minus a. And see, the singularity is actually symbol pole. So in that case, what we really need to do is we multiply with the t minus minus a and evaluate the limit t tending to minus a of the whatever which is remaining. So if you multiply this function with the t minus minus a, you will see that basically the t plus a you are multiplying. That will cancel with the denominator and you will get just t raised to alpha minus 1. So t raised to alpha minus 1 in the limit of t tending to minus a. So you will see it's 2 pi I times minus a the whole raised to alpha minus 1. So the minus so okay, so a raised to alpha minus 1 I can take outside, then the minus 1 the whole raised to alpha minus 1. So that what we can do is we can write minus 1 as e raised to I pi and then the whole raised to alpha minus 1, so which we can simplify to 2 pi I times a raised to alpha minus 1 e raised to I pi alpha times e raised to minus I pi, right, e raised to minus I pi. So e raised to minus I pi is just cos pi minus I sin pi, which is just minus 1. So that I will keep here. So we have evaluated the right hand side also for the equation 4. Now we substitute all the quantities on the left and right hand side of the equation 4. So remember, equation 4 comes from the residue theorem. I mean, basically the contour integral theorem. It's a theory for the contour integrals. So so from the equation 4, what we find is that the expression of the integral over arc 1, arc 2, then line 1 plus line 2 is equal to 2 pi I times the residue, and which is basically the contribution from arc 1 is 0, contribution from arc 2 is also 0, and contribution from line 1 is basically I, which is of alpha and a, and contribution from line 2 is basically minus e raised to 2 pi I alpha of the same integral I of alpha comma a. On the right hand side, we will find it is minus 2 pi I times a raised to alpha minus 1 e raised to I pi alpha. So for this we also return to conditions that alpha should be less than 1, should be greater than 0, then only this is valid. Otherwise you may have some extra contribution from the arc 1 and arc 2. Specifically for the case of alpha equal to 0 and alpha equal to 1, we have seen such case exists. And remember, when alpha is outside this range, you may find this integral does not converge. Okay, so for alpha at the extreme condition of equal to 0 or equal to 1, you find a modified result because of the contribution from arc 1, contribution from arc 1 or arc 2. But if it is lying outside this interval, you may not find a finite result. I mean, maybe it is a diverging quantity. So yeah, so let us group this. We will find this integral I of alpha comma a times 1 minus e raised to 2 pi I alpha, which is equal to minus 2 pi I times a raised to alpha minus 1 e raised to I pi alpha. So that I of alpha comma a is minus 2 pi I a raised to alpha minus 1 e raised to I pi alpha divided by 1 minus e raised to 2 pi I alpha. So let me take this minus in the denominator. We will see this is this, and you can also divide with e raised to I pi alpha in the numerator and in the denominator. So why I do is that you will see now. Just simplifying it to a simple expression. So this you can rearrange. You can take the pi a raised to alpha minus 1 outside, then the remaining term 2y divided by e raised to I pi alpha minus e raised to minus I pi alpha, which will take together. Remember that sine theta is actually e raised to I theta minus e raised to minus I theta by 2y, which we use here because we have similar form, just that it is inversed, or it's reciprocal axis here. So it's basically 1 by sine of pi alpha, which is cosec pi alpha. So pi a raised to alpha minus 1 cosec of pi alpha. So we find that I of alpha comma a, which is basically the integral t raised to alpha minus 1 by t plus a dt from 0 to infinity, is pi a raised to alpha minus 1 cosec of pi alpha for any real value of a, and alpha should be less than 1 and greater than 0, alpha element of real number, similarly a element of real number. So we find this is the solution. But so this is just the expression I of a comma alpha, or alpha comma a. But from expression 2 we need I of alpha comma z also, and we know they will be basically identical, just that a will be replaced with z. So I of alpha comma z is going to be pi of z raised to alpha minus 1 cosec of pi alpha. Then from 2 we will find that the Stieltjes transform of the function is a minus z, the whole inverse. From 2, let me see again. So I of alpha z minus I of alpha a. So I of alpha z is pi z raised to alpha minus 1 cosec of pi alpha. Then I of alpha a, which is pi a raised to alpha minus 1 cosec of pi alpha. Now you can take the common terms outside, then you will find this is the solution. So which is basically the Stieltjes transform of the function which is asked for. Okay, so is this clear? Any doubt? Okay, so if there is no doubt, we will move to the next problem. Which of the following is or are the Stieltjes transform of the function 1 by t square plus a square? So this is actually similar compared to the earlier one. We don't need to go to any complex domain, just the real domain itself enough. But we have to remember certain things. I mean, basically applying the limits, we have to take a little complicated. Not complicated, but we have to be careful. Okay, so from the definition, the Stieltjes transform of the function f of t is 1 by t square plus a square times dt by t plus z integral 0 to infinity. Okay, so unlike the earlier case, we don't have any t raised to alpha minus 1 here. So everything is like integers, the powers of t. So we can do this integral. I mean, can be done in complex domain also, but we don't need to go there. We can actually perform this in the real world itself. Just we need to do the partial fraction of this quantity 1 by t square plus a square times t plus z. Remember, t is the integration variable, a and z are numbers. So this we can split into a divided by t plus z plus bt plus c divided by t square plus a square. So you will find a, which is equal to 1 by a square plus z square, b, which is equal to minus 1 by a square plus z square, then c, which is z divided by a square plus z square. So let me denote this expression as 1. So from the 1, equation 1, if we substitute these values there, we will find basically the Stieltjes transform of the function f of t is the integral 0 to infinity a divided by t plus z. So it's a square plus z square inverse, the whole divided by t plus z. Then b, which is minus a square plus z square the whole inverse. So bt, right? So it's b t by t square plus a square. Then c, which is z, a square plus z square inverse by t square plus a square dt. So this is actually we convert into three separate integrals. So we can perform them separately, but remember that there's an issue while applying the limits of the integration. So I will explain that. First we perform the integral separately. So first of all, a square plus z square inverse, which is a constant taken outside, then dt by t plus z integral 0 to infinity. Then second, a square plus z square inverse is again a constant, then integral t by t square plus a square dt 0 to infinity. Third one is z, a square plus z square inverse dt by t square plus a square integral 0 to infinity. So the first one, a square plus z square inverse, first integral is basically 1 by t plus z. So the integral will be just log of t plus z because its derivative is appearing in the numerator, just 1, right? So it's a log of t plus z. Just that the limit t equal to 0 to infinity that we need to apply. That there is an issue, we cannot apply it right now. If you apply right now, it's log infinity minus log 0 plus z, which is log infinity minus log z, and log infinity does not have a definite value. Basically it's infinite, right? So which may say that okay, it's diverging, wait for it. So that's why we are not applying the limits now. I mean, we can, but we are to take care of certain things, like there is an infinity appearing, log infinity appearing here, which is going to cancel with another log infinity. For that we have to properly take the limit. Instead of putting the higher limit to be infinity, we have to actually put that cell as, let's say, capital R, and then take the limit of capital R to be infinity. Properly we need to do that, but instead I am doing a different thing, like we are grouping terms which if they group together this at the infinity, we don't need to take a separate limit, it will automatically going to cancel. So that's what I am going to do. Okay, anyway, from the second integral you will see it's a square plus z square inverse is a constant, and it's a t divided by t square plus a square. So we make it in a way that, so in the denominator we have t square plus a square, its derivative is 2t. So let's make the numerator in such a way that derivative of the denominator appears in the numerator. If that is the second integral can be written as a square plus z square inverse half then integral of 2t dt divided by t square plus a square. So now the denominator is t square plus a square, its derivative 2t is appearing in the numerator, so the integral will be just log modulus of t square plus a square. And this actually this half can be taken inside by manipulating, or not manipulating, using the properties of the log, which will appear as a square root for this expression. Then the third integral is actually easier, right? It's actually 1 by t square plus a square, so it's 1 by a tan inverse of t by a. Just that we need to apply the limit of t is equal to 0 to infinity. In the second integral also we need to apply the limit, t goes from 0 to infinity. Now like I said earlier, so in the second integral also there is going to be a log infinity come while applying the limits. So we combine the first and second results together so that the log infinity will not appear. Third integral can exist, I mean the third result, which at the infinity also is not going to diverge, and at 0 also not going to diverge, so we can directly apply the limits. Just that the first two integral that we need to combine together. So basically a square plus z square inverse is a common for both. Then log of t plus z, using the properties of log, we can write it as like this, and then apply the limit of t is going from 0 to infinity. Then plus the third one is z square plus, okay, z divided by a square plus z square 1 by a, then tan inverse of t by a, where t is going from 0 to infinity. Now we can apply the limits. Before that, the most common thing, which is 1 by a square plus z square, which I will take outside. Then here it's a log of 1 at when t is going to be infinity for any finite value of a and z, minus log of z divided by a plus z by a times tan inverse of infinity, which is pi by 2, minus tan inverse of 0, which is 0, and log 1 is 0. So we'll find the solution to be 1 by a square plus z square times pi z by 2a minus log of z by a. So it's actually simple. I mean, we are just using the normal calculus, basically the real calculus. We are not using any complex thing, but just that we need to be careful with the limits. That's all. So I think this is clear. This is clear. Any doubt? Okay, so then we'll move to the next problem. Find the Hilbert transform of the function f of t exponential of I omega t. So from definition, the Hilbert transform of a function f of t will be, so it's actually the integral, so it's looking like Stieltjes transform. So f of t divided by t minus x dt. So here we are doing the integral, the transformation from the variable t to x. So the definition will be f of t divided by t minus x dt integral. Unlike earlier, here the limit of t is minus infinity to plus infinity. At that time, when t passes through x for a real number x, you will find there is an issue. So then we need to use a cautious principal value integral. We are actually excluding the location x, just like we integrate from minus infinity to x minus epsilon, then x plus epsilon to infinity, excluding the location x. That's a principal value, cautious principal value integral. Then we scale it with the pi. So this is the Hilbert transform. So here we have the function exponential of I omega t, where omega is some real number. So we'll apply the expression. We'll find this is e raised to I omega t divided by t minus x dt. So this is the integral that we need to perform. So like earlier, we cannot do this in complex. We cannot do this in the real world. So we need to go to the complex world. So for that, consider this function, or consider this integral. Let's say I, or let's say j itself. J is now an integral e raised to I omega t divided by t minus x dt, where x is some number. T is the number which we are going to expand it to the complex domain. T is actually the integration variable. We are going to expand it to the complex domain. So j is an integral of the same function over the complex, over the contour, closed contour in the complex plane. Let me draw the contour. So we have to choose a contour which will benefit us in terms of evaluating this integral, right? So basically the x-axis is real of t and y-axis is imaginary of t. So the function has a singularity at t equal to x, where for some real number x, let's say x is a positive real number for the moment. So at x, it has a singularity. Okay, it's a simple pole. And the remaining nowhere you will find a singularity, because the exponential of I omega t is actually an entire function which is analytic everywhere. So just that 1 by t minus x has a singularity as at t equal to x, that we have denoted. Now nowhere else it is singular. We need to do the integration from minus infinity to plus infinity. So we actually need to do the integration over this line, excluding the location x. So we choose a contour which skips this x. So one possibility is this contour, and there's another possibility. So this is another closed contour. So there's another possibility that also I will draw. We need to use that. So I will tell, probably because we are running out of time, I may not be able to finish everything, but I will tell how to do this. You can try yourself. So again, x is positive. Look, at t equal to x, you will find a singular point. We need to do the integral over this line, excluding the location at x. See, this works even if x is a negative real number. Okay, doesn't matter. But only thing we need to take care of, the sign of omega. Omega is a real number, but sign of omega matters. That I will show anyway. So this is one of the contour. Another contour is this one. Both are okay, but there are specific cases we need to use. So this is when omega is greater than 0, and this contour when omega is less than 0. So why such a distinction? That probably I will tell now, but I will show for omega greater than 0 and omega less than 0. You can try it yourself, identical, just that you change the contour. So let's say this is first quadrant, second quadrant, third quadrant, and fourth quadrant, right? This is okay. I will call the entire contour. It's actually in the upper half plane. Let's say I call that contour as gamma, and this one arc 1, and this is arc 2, and this one line 1, and this one line 2. So over the gamma integral that we need to perform. So the integral over gamma of the function can be split into 4 parts: integral over arc 1 plus integral over arc 2 plus integral over line 1 plus integral over line 2. Now the solution is actually equal to 0 from the Cauchy's theorem, because there is no singularity x is inside this contour. This contour is actually chosen counterclockwise, and you will find no singularities inside the contour. The only singularity which is at t equal to x, which is actually lying outside the contour. So we'll find this expression should be equal to 0. So from the Cauchy's theorem, if there is no singularities, the integral over the closed contour will be 0. So we have no singularities inside this closed contour gamma, so that we find this expression to be equal to 0, and the integral over arc 1. And so basically, okay, let me show for arc 1 how it works. Let's say it has a radius of r, so it's minus r here, plus r here, then ir here. So the t is actually equal to r e raised to I theta, where theta is going from 0 to pi. Okay, and r in the limit is actually tending to infinity. So integral over arc 1 is actually limit capital R tending to infinity. So the function is e raised to I omega t, which is r e raised to I theta, which I can write it as r cos theta plus I sin theta, right? because it's appearing as an exponential, I am just expanding it. Okay, then dt will r e raised to I theta I d theta, then whole divided by t minus x, which is r e raised to I theta minus x. Like earlier, for any finite value of x, when r tending to infinity, you will find the r e raised to the numerator and denominator will cancel, and this will appear just limit r tending to infinity. Okay, and theta is going from 0 to pi. I forgot to write that. So theta is going from 0 to pi, e raised to I omega r cos theta, e raised to minus I omega r sin theta d theta, and I is a constant. You see, this is an oscillatory part, and this part can grow exponential or decay exponential. Just that r is positive, sin theta is positive in 1 and 2, omega is also positive. That means integral over arc 1 should 0 when r tending to infinity. If omega was negative, then this will diverge exponentially. So that's why for omega positive, we have chosen this contour. In 1 and 2, sin theta is positive. That's why this combination become exponentially decaying. Okay, forgot. Yeah, that I is not there. It's an exponential of minus omega r sin theta. Similarly, arc 2 you can so integral over arc 2, which will be limit epsilon tending to 0. So there is one thing that okay, let me write that. So for arc 2, see, it's not actually a circle which is centered about the origin. It's a semicircle, of course, but it's actually shifted semicircle in the x-axis. So its origin is actually shifted. So we have to write it that way. T is equal to x shifted with a radius epsilon e raised to I theta. And also its orientation is not from 0 to pi, rather it is from pi to 0. It's a clockwise terms. So theta is going from pi to 0 and epsilon tending to 0 for any finite value of x. So the integral over arc 2 will be limit epsilon tending to 0 integral theta is going from pi to 0. Again, it's e raised to I omega t. So it's a exponential of I omega times t, which is x plus epsilon cos theta plus I epsilon sin theta, then dt, which is epsilon e raised to I theta I d theta divided by t minus x. So it's a t minus t minus x, where t is x plus epsilon e raised to I theta. So t minus x will be epsilon e raised to I theta. Now this epsilon e raised to I theta, this epsilon e raised to I theta will cancel, and we can reverse the integral to 0 to pi with putting a sign in front, and also we take the limit of epsilon tending to 0. We will get it is e raised to I omega x then I d theta, and see, there is no other theta dependence here, so we can actually validate this expression as here minus I e raised to I omega x times pi, because it's integral d theta from 0 to pi, and we will find this is pi. So this is the solution or contribution from arc2, which is non-zero. Now line 1 plus line 2, you can actually see they combine and give the expression that we actually want, which is this one. So let's say this is capital F of x. We will get this as pi times f of x as the integral. Oh, sorry, capital F of x from the definition. So now from this expression, let's say this is expression 1. Okay, let's say this is 1, and this is 2. So this is basically using 1 from 2. we will find the contribution of arc 1, which is 0, the contribution of arc 2, which is minus I pi e raised to I omega x, which is equal to pi times f of x. Did I made any mistake? Let me check. Yeah, it's right. So oh sorry, yeah, here I made a mistake. Yeah, sorry. Plus pi times capital F of x equal to 0 from equation 2. Now if you rearrange, you will find f of x, which is basically the Hilbert transform of the function f of t, or the Hilbert transform of e raised to I omega t from the variable t to x. You will find this actually, okay, let me write f of x here. It's cancelling I pi, it's I e raised to I omega x. So it is I e raised to I omega x. So but thing is that this is possible if omega is greater than 0. If omega was less than 0, then use this contour, okay. Because in omega is less than 0, we cannot use the first contour that I have drawn. You have to use the second one, because in that case the integral over the circular arc, otherwise it will be divergent. So you have to use the second contour, and you will be able to show that there you will find the Hilbert transform of e raised to I omega t will be minus I e raised to I omega x if omega is less than 0. Okay. Use use omega. Let me say this is omega. This was gamma. So this was we had to use here omega. Generally, then we can say the Hilbert transform of e raised to I omega x or I omega t is sine of omega times I times e raised to I omega x. Okay. So is this clear? Okay. So if no doubts, we'll stop here for today. So we'll meet next week then. Okay. Thank you.